Hello, this is Jeremy. A few weeks ago, I saw someone place a C style of reversing an array in place. And I would like to refactor that code to show how more modern C++ principles can avoid some of the nasty memory pitfalls that a C style C++ can bring you. When you're in a specialized environment, absolutely you have to write things in this lower level. But application code, or when you're outside that area of speciality, you can use more of a modern C++. Bjarne Stroustrup, the author of C++, says, if you write C-style C++, you're going to have C-style problems. And one of the things he means by that is you're going to have more memory problems, access violations, segmentation faults, illegal operation errors. When you use more of a C++ style, you get more compiler errors, but those compiler errors are of course at compile time, which means that you, the programmer, can work through them. So we're going to start with the code. As it was at the end of the previous video, I'll link to it. And after that, we'll incrementally refactor it toward a more modern style. At any point along this refactor, we could stop and say this is the style that we want to embrace. We're eventually going to get to the point down to just two single functions, essentially, to do our total output using the standard template library, which is C++'s standard library. Alright, so let's go. So first, let's just kind of make sure this works. So we'll build this. Okay, built, and then we can run our application, and it runs. We can see that that's the reverse of this right there. Okay. So the first step, Vim habits. The first step is to add unit testing. Anytime you're going to refactor something, you always add unit testing. So let's start there. So let's go grab my favorite unit test library, Catch. So then that just downloaded to Documents, Catch, and we'll put it in our source folder. Okay, so now we have Catch. Catch works by including it. The entire library is in fact in the header file, and we have to tell Catch that we want it to provide the main. So we're going to define Catch with main. I think that's what it is. Catch config main. Okay. Okay. Now, since Catch is going to provide a main, we need to refactor this to actually be a test, because this is kind of our test runner. So this is a test case, and this is our old main file. Okay. And then we can call this runner. These are tags, can get useful when you have lots of tests. And then we don't need to return anything. Okay. So we can build this. Building is a bit slower. Catch is somewhat of a large library, somewhat. Now we need to run it. So we're going to run our unit tests, edit configurations. We're going to add a catch runner, all reverse in place. We're just going to run all the tests, and we'll click OK. And then we'll say run that. Okay, and it printed. So now a test case isn't a test case unless we assert something. So let's write our assertion. We require that the initial value of the array is in fact 10. Okay. So we expect this to reverse and then that value to be 10. Let's try it again. Okay, so then our test ran. Just to kind of see that we're on the right track, let's actually watch this test fail. Okay, I'm back. My girls decided the floor was hot lava and they were coming to save me. Okay, so let's go ahead and change this back. Now this is getting pretty exhausting, rebuilding every single time. Catch isn't changing, so we actually only need to compile it once. So let's create a source file called buildfaster. And what buildfaster will do is we'll actually move the catch library there. Oops. Okay. Now we still need the header file, but we don't need to define main more than once. And when we build this, this will build and link one time. Okay. And let's change it and watch how quickly it builds the second time. Much faster. Okay. We have our great little test results, and then we can, run just like that. Wonderful. So we have a much faster build process now. Okay, so let's start by refactoring this with a more modern style. First thing to do is the compiler doesn't actually need this type here. It knows that it's ints. We can just call it int. And then we can use uniform initialization. Okay. So the first step here is we actually have quite a bit of code here. So let's refactor this test a little more. Let's create this in a function called reverse. And it will take an int array. And then let's actually move the declaration of this array. And this is actually going to point out one of the C-style problems. So then we'll call reverse array. And we expect this test to pass, when in fact we'll actually get a memory fault, probably. There it is. So something bad happened. What is that thing? The problem is that an array doesn't know how big it is. So this size of, while it worked when the array was initialized right above because of compiler magic, when it's passed through as an argument, it no longer knows how big array is, and instead it takes the size of the pointer to the array, which of course is just an int pointer. So what this actually is an int pointer, and that actually looks more suspicious. So in C style, you always have to pass the length with it. So this is 10. And then we'll actually see this work again. All right. And we have our test again. Another thing is sometimes code can depend on something being an odd or an even length. So let's just make sure that as we're refactoring, all of these cases work. Okay. And let's test them as well. I'll reverse in place. We'll run all these test cases. Great. So now we have 2. Okay, and they're all passing. So in C++ we have a type called size t, which is supposed to be saved for the size of things, and there's certain guarantees in the standard that it will be big enough. But it's also never negative, so a size can't be negative, and so it actually helps declare intent. So that's a nice little artifact. You want the types to declare what they're supposed to do. Okay. So now we have our array. We have to pass a size because the compiler magic trick only works once when we were doing that little size of magic. Instead, we have to actually start passing the size, and so we've done that. So now we can actually start working on this guy, swap, which takes an array and a left and a right. In fact, there is a standard swap in the standard template library, so we don't need this. We could just include utility and iterator, and then we actually have standard swap available that takes 2 pointers. So then we have to refactor this to work with pointers. So we could change this back to an int pointer. This is pointing to the beginning of the array. Okay. This will become an int pointer pointing to the end of the array. We can just do array plus length. So take the array pointer, increment to the size of the array, and then -1. And then we can swap these 2 things. Okay. Let's try this, see what happens. Alright. So that's swapping the pointers, but we actually want to swap the value of the pointers. And our code works. And we've made it a little shorter, a little simpler. So this is still a very C style, but we've erased a custom function that was duplicating functionality. We now are depending on a standard library. We're swapping the values in those 2 positions. And it works for both the even case and the odd case. So that's pretty nice. So now we have a choice. We can say, this is pretty good, this is done. Or we can keep going and refactor away all of these pointers and use iterators. And what will happen is we'll do that in 2 steps. We'll refactor the iterators away, and it'll seem to be a little more complex. But then we'll take it one more step, and it'll be vastly simplified. Okay? So the first thing to do is to recognize that this array here, there's really no reason it can't be a vector. So let's just make it a vector. So vector is the standard template library's utility data structure. It's extremely fast. It's dynamic. And it carries its own size with it, which is nice. Now if you wanted a static vector, that can be done. There is an array type, but you have to carry the size along with it. One of the general patterns in C++ is if you want your code to be fast, just use vector. If you really can't afford the dynamic allocation, then there are other data structures available, but you can always just pass vectors by const. And that works as well. Okay. So let's refactor this to actually take a vector. And then we don't need this size anymore. Okay. So this is just going to be array.size. Okay. And we'll refactor this later. So the first step is, instead of using an int pointer, we're going to use an iterator. So this just becomes auto, and we want an iterator at the begin of the array. You can also call array.begin. I personally like to use the non-member version because it works in more useful cases. Okay. So this would be the standard pattern. However, our algorithm depends on the I pointer moving forward and the j pointer moving backwards. And the end pointer doesn't actually move backwards, so we need the beginning of the end, which is called the reverse begin. So that's an iterator that, when incremented, moves backwards. So it's the beginning of the end, or the reverse begin. Okay. And so our while statement is actually going to be while the distance of the beginning of the array to I is less than the array.size divided by 2. So we're going to move I until the end. We want to swap the value at I, the value at j. And then we're going to both increment I and increment j. So here's our old code. We'll just kind of knock that out so we can look and compare with it. So the middle is actually the same. We just have this new little mess here. And this is actually a lot more stable. So if you happen to be on an architecture where pointers didn't lay out in the order that you believe they did, where the beginning is a lesser value than the end, memory could be laid out in a different address space. This is actually comparing memory addresses here on line 36. And that addressing order is actually not guaranteed. So if you happen to be an architecture where that wouldn't be true, this code would no longer work. This works independent of memory architecture. Okay, so we'll compile this and we'll run it to see that it doesn't explode. Okay, so we got some compiler errors. No matching function for reverse standard reference. Okay, so we're going to do that. And we're going to do that. Okay. Line 61, got some more compiler errors. And we need to refactor this one as well. Okay. Now what's happening here? It seems to be the same as before. We're passing the array, but the value isn't changing. Is our code broken? No. The problem here is subtle. Before we were passing it by pointer. We were passing something by reference. Here, we're actually passing by value. So C++ is making a copy of the array here and sending in the copy. The copy gets sorted, but then nothing happens to it. And so this value stays the same. So instead, we need to pass by reference. So don't make a copy of this array. Just send it through by reference. Okay. And now everything is passing. So let's go fix our, we can remove this, get it out of the way. And let's go fix our print array. Okay. So we're going to take a vector events of our array. We don't need our length anymore because array knows how long something is. Now we can implement this in a couple different ways. So let's go take it one step at a time. And let's put a new line at the end of this because that was kind of irritating me before. So we don't need this raw indexed kind of style. We can use a ranged base 4 where we just take the value, each value of I over the array. Now we're going to have each value I in our little I there. Okay. And let's just see what this does for now. So incremental. Okay, cool. Code compiled. Let's actually try and print it. Great. We need to put our commas back in. So if I is less than the length, well, I is actually the value now. So let's just delete this for now, which is going to put a comma after every value, which is going to be slightly annoying, and then we're going to make it prettier. Okay, cool. So now we have this comma space at the end, which is ugly, but our code is almost working again. Now, let's make the same refactor. Let's refactor for iterators. And let's use a stream joiner, which is a little trick in the standard template library. So we're going to knock this guy out, and we're going to go put our own value in right here. So we are going to take the values and copy them from the array to the stream joiner. Let's see how that works. So we're going to copy. We're going to need an algorithm. Okay. A friend of mine calls this import brain. Okay. Array to standard end array. And here's the magic part. we are going to copy each value from the beginning to the end to the experimental make ostream joiner, and we're going to copy those values to standard out, appended by space. Okay? Oops, wrong place. So we're going to copy from the beginning to the end, copy each of those values into the ostream joiner, which is going to write to standard out. So let's try this. Yep, it's happy. And we printed our values, and that little comma at the end's gone. So we could compare these, run again, and run again. Okay. Much shorter, much more idiomatic, clean. Now, why didn't we have to pass this by reference? Because we're not changing it. We don't need a reference to it, but it is somewhat less efficient to make a copy of that array. So instead, let's pass it by reference, but tell the caller we're not going to change it. So we'll pass by reference to const. And const is right-hand associative, so it needs to go on the right-hand side of the thing it applies to. So constness always applies that direction. And we'll run this again. Okay. So now we have our print array, a lot cleaner. And we have this reverse algorithm to us, still written in somewhat of a verbose style, doing swaps manually. C++ actually defines this for us in the standard template library. Okay. As the reverse function. We can reverse from the beginning to the end. Let's keep those. Actually, they were different, huh? From the beginning to the end. And that's it, actually. Run this. Looks good. Run this. Looks good. Okay. So much shorter. Actually, notice how the code fits all on one page now. And it's doing the same thing we started in the beginning, except now we actually have unit testing. And we're done. Thank you everyone for checking out my modern C++ refactor of in-place reverse.